Why channel spacing between macros is crucial in VLSI design, showing the question. The question you asked highlights a fundamental aspect of floor planning. Channel spacing, the distance between macros in a VLSI design, is crucial for ensuring efficient routing and overall chip performance. Reasons for channel spacing. Routing congestion. Providing adequate space between macros allows for sufficient routing channels. These channels accommodate the interconnections between standard cells, macros, and I/O pads. Insufficient spacing can lead to routing congestion, where there's not enough room to route wires, resulting in longer and less reliable connections. Signal integrity. Proper channel spacing helps maintain signal integrity. It reduces the likelihood of crosstalk between signals, ensuring reliable data transmission. Power and ground distribution. Sufficient space between macros allows for proper routing of power and ground lines, preventing voltage drops and ensuring stable power supply to the entire chip. Thermal management. Adequate spacing aids in heat dissipation. It prevents hotspots and improves overall thermal performance of the chip. Design for manufacturability, DFM, channel spacing helps maintain design rules and ensures manufacturability. It prevents short circuits and other fabrication-related issues. Determining channel spacing. The optimal channel spacing depends on various factors. Number of pins on macros. More pins typically require wider channels. Expected routing density. Areas with higher interconnection density require wider channels. Design complexity. Larger and more complex designs might need wider channels to accommodate complex routing. Technology node. The specific fabrication technology used influences the minimum allowed spacing between metal layers. Conclusion. Channel spacing is a critical consideration in floor planning. It directly impacts routability, signal integrity, power distribution, and overall chip performance. By carefully determining and maintaining appropriate channel spacing, designers can significantly improve the quality of the final VLSI design. Arranging macros in a macro-dense partition, showing the question. Arranging macros in a macro-dense partition is a critical challenge in VLSI floor planning. Here are some strategies to optimize macro placement. 1. Macro clustering. Functionality-based grouping. Group macros with similar functionality or high interconnectivity to minimize wire length. Timing-driven clustering. Place timing-critical macros closer together to reduce signal delays. 2. Macro orientation. Optimal placement. Choose the best orientation for each macro, horizontal or vertical, to minimize area utilization and facilitate routing. Avoid obstructions. Consider the impact of macro orientation on routing channels and power, ground distribution. 3. Channel placement. Sufficient space. Ensure adequate channel spacing between macros to accommodate routing congestion. Power and ground routing. Consider the placement of power and ground rails within the channels to minimize IR drop. 4. Macro shaping. Flexibility. If allowed by the design, consider shaping macros to fit within the available space more efficiently. This can help reduce wasted area. 5. Floor planning tools. Automated placement. Utilize advanced floor planning tools that employ algorithms for optimal macro placement, considering timing, power, and area constraints. Iterative refinement. Continuously evaluate the floor plan and make adjustments based on simulation and analysis results. 6. Additional considerations. Power and ground distribution. Ensure proper placement of power and ground pads to minimize IR drop and electromigration. Thermal management. Consider the placement of heat-generating macros to avoid hotspots. Clock distribution. Plan for efficient clock tree routing by considering macro placement and channel locations. 7. Design for manufacturability, DFM. Adhere to design rules. Ensure the macro placement adheres to design rules for spacing, overlap, and other geometric constraints. Consider manufacturing variations. Account for potential variations in manufacturing processes that might impact macro placement and performance. 8. Iteration and optimization. Floor planning is an iterative process. Continuously evaluate and refine the macro placement based on simulation and analysis results. By carefully considering these factors and utilizing advanced floor planning tools, you can effectively arrange macros in a macro-dense partition to achieve optimal chip performance and manufacturability.